G'day viewers. In this segment we'll talk about the sliding window algorithm for reliable data transfer. So the sliding window is one of the most well-known algorithms in computer networking. It combines pipelining for performance with reliability. And it does this by building on what we've seen before, the stop and wait algorithm, which used ARQ, automatic repeat request, with a window size of 1. Okay, so let me go back there and start at the beginning. I said that ARQ, automatic repeat request, well, that's a mechanism that provides reliability by retransmitting packets or segments or frames, depending what layer you're operating at, until they're acknowledged by the other side. So it ensures they'll get through. Now with stop and wait, which we saw before, only one message can be outstanding at a time. Here's the time sequence diagram for the normal case where nothing is lost. You can see the sender sends a frame and it numbers it, number 0, and that comes back, and then we're happy. The sender knows that frame has made it to the receiver, so the sender can move on and send the next frame. That's frame 1, and an ACK will come back for it eventually, and so forth. There's a big limitation of stop and wait, however, and that's the fact that only one frame can be outstanding in the network at a given time, at any time. Now, this is fine if we're talking about a local area network, because the propagation delay over a local area network is usually small enough that that sending a single packet fills that network. It uses it well. On the other hand, imagine an internet path where we might have a bandwidth delay which is much greater than one packet. In this case, the packet will only fill a very small portion of the network path and will be using the network inefficiently. This is similar to the picture you can see here, in which there's just this small packet in the midst of a long network path between two hosts. So let's take a look at how much of a limitation this is. Imagine that we have a network with a rate of 1 megabit per second, that's the capacity of the network, and the propagation delay is 50 milliseconds. So the round trip time will be 100 milliseconds. How many packets a second can we transfer reliably over this network using using stop and wait, which will turn out to be a sliding window of size 1. Well, I can see by inspection that if it takes 100 milliseconds, that's 1/10 of a second to send a bit to the other side and back, then at most we'll be able to send 10 packets a second. Now, if every packet is 1250 bytes, chosen so that's 10 kilobits, that is going to be an information transfer rate of 100 kilobits a second. That's not much considering that the network path could handle a megabit per second. So we're only using a fraction of it. We're using about 10% of the network path's bandwidth. Suppose we upgrade the link to be 10 megabits per second because we just want everything to be faster. How many packets could we send? Again, the answer is 10 packets a second. Why? Because they were constrained by the round trip time. The bandwidth really didn't affect them at all. This is going to be the same, 100 kilobits a second. And now it's actually going to be more like 1% of the capacity instead of 10%. So for our fast and long networks, stop and wait really uses them inefficiently. Okay, so sliding window generalizes stop and wait and considers that to be the special case of a window size of 1. With sliding window, we'll allow a window of up to W packets to be outstanding at any given time. By the way, I'll talk for the sliding window about either frames, packets, or segments as is convenient, since this algorithm could be used at either the link, network, or transport layers. We're really using it at the transport layer, that's what TCP does. But since we're building on ARQ and we saw that at the link layer, you'll still see frames, and I'll sometimes talk about packets. Now, with a sliding window and a window of size W, that means we'll be able to send W packets per round trip time. The pipelining here that we're getting by sending multiple packets at once is what's improving performance for us on the network. To use the entire network path, so if I have a rate of 10 megabits per second, to use all of that, then I would want the window to be large enough so that I could send so that it is the same as 2BD expressed in packets. The reason for this is that we said you can send W packets per round trip time. A round trip time is really 2D. If we want to send it the bandwidth, the full rate, then we want to send B bits per second for those RTT seconds. Multiplying it all together, we get 2D up here times B for the bandwidth, which is 2BD. That's the amount of data that can be transferred over the path in one round trip time. So if we set W to that, we'll be able to send at that rate. Let's see what kind of window sizes this implies to get it working. So what window size W would we like to use to fill up the network, to use it to its capacity? For the examples before, now with a rate of 1 megabit per second and a delay of 50 milliseconds. So we would like W to be equal to 2BD, that is twice the bandwidth times the delay. I'm just going to multiply the bandwidth first, that's 10 to the 6 bits per second, and twice the delay is 100 milliseconds, so that's 100, like 10 to the minus 3 seconds. So that's 100 kilobits. Kilobit. Now expressed in packets, if a packet is about 10 kilobit, that's 1250 bytes. This is about 10 packets. So to use the path fully, we needed to have a sliding window size W of about 10 packets rather than the one packet in stop and wait. And this is what you might imagine, since we worked out before, we're only getting to utilize about 10% of its bandwidth. So we were off by a factor of 10. Now, what if we increase the rate to 10 megabits per second? Well, I could do my W equals 2BD calculation again. This is a W. And actually, the only thing that's happened is the rate, which is the B in this equation, has gone up by a factor of 10. So it's going to be 1000 kilobit, or approximately 100 packets. So you can see that I would need a reasonably sized sliding window to fully utilize this link, and the sliding window would just have to get bigger for faster and longer links. Okay, so here's all of this tidied up, and hopefully I got all of the math right. So let's now talk about the sliding window protocol in a little more detail. We've just said that there are these W packets outstanding, but how exactly does it work? Actually, there are many variations of the sliding window protocol, depending on exactly the way you want to handle the buffering, the acknowledgements, and the retransmissions. I'm going to sketch for you two versions. One is called Go Back N. This is the simplest version. It's not terribly efficient when there are errors, but it's quite simple and you don't have to do much at the receiver or sender. And I'll also talk about a version called Selective Repeat, which is a little more involved, especially at the receiver. But on the other hand, it gives us slightly better performance. Or actually, it could be a lot better performance in the case when there are errors. So this is what happens at the sender. Now, the picture below is showing you the buffering as a function of the sequence number space. So sequence numbers go up to the right here. So this is the segments of data go along to the right here in this picture. The sender is allowed to buffer up to W segments of data until they're acknowledged. So this is information that's been sent and not yet been acknowledged. The sender needs to buffer this because if it's not acknowledged, the sender is going to have to retransmit it, so I better have a copy. We'll express the sliding window with a couple of sequence variables, a couple of state variables. One is going to be LFS, that's the last frame sent. That's here, so it's the highest numbered segment which has actually been sent out but not yet acknowledged. The other variable is LAR, the last acknowledgement received. So that's the number of the highest in-sequence acknowledgement which has been received from the other side. And our sliding window allows us to, it has a buffer of up to W packets, so we can have a difference between LAR and LFS, that's the number of packets we've sent into the network that haven't been acknowledged, of up to W packets. You can see here is the sliding window here, and we actually have 4 packets out in the network, the window's 5, so actually we could fit one more. All of the segments before the left side of this window, we're finished with them. They've all been sent through the network, acknowledged by the other side. We've got the acknowledgement. They're done. They're finished. And to the right side of this sliding window, there's segments that we can't yet send because our window is not big enough. Okay, so this is the sliding window. It evolves as we send new packets and receive ACKs. So a couple of things could happen here. What could happen? Well, one thing that could happen is the transport layer could accept another segment from the application, and that would be this segment here. And in this case, it can go ahead and send it. Why? Because we only had 4 packets outstanding in the network, and our sliding window size is 5. If we send this one, now we have 5. And you can see I've updated LFS here. I haven't updated LAR because we haven't received any acknowledgements. So now our window is full. At this stage, we can't send any more segments, new segments, into the network until some of the old segments which are in the network are acknowledged. Here's something else that can happen. We can receive the next higher acknowledgement. Now, you might have noticed that LAR has moved along. We actually received an acknowledgement for this packet here, this segment here. So LAR now points here. I've not colored that pink anymore because we can free that buffer and throw it away. So in fact, now we only have these 4 segments outstanding in the network. And you can see that this sliding window is still size 5, but it's slid to the right. That's why it's called a sliding window. It moves along. That's opened up space for us to send one new segment into the network. And there you are. That's how the sliding window is operating in the normal case. At the sender, you can see it moving along, sending new segments into the network as old segments are acknowledged. Let's look at what goes on at the receiver, because we just saw the sender half there. And recall I was going to describe 2 different variations for you. The first variation is go back in. And it's very simple. It's actually the simplest sliding window receiver implementation. Here, the receiver only keeps a single packet buffer, segment buffer, to put the next segment in. So it passes, when it gets the next segment, the right segment, it passes it up to the application. So the application sees data in order. All we need here is one state variable, LAS, the last ACK sent. And what we're looking to do is receive a segment which is the next one beyond that. So this is what happens when a segment is received. We look at the sequence number. If it is the next one, then we accept it. We put it in the buffer. We pass it up to the app as soon as the app can take it. We update LAS. This is now climbed up by 1. And then we send an acknowledgement to the other side to say, yep, got LAS plus 1. If the sequence number is anything else, then we can simply discard it and not worry about it. In effect, there has been some kind of error. If it's something else, then a segment has been lost in the network. And the sender is going to work that out and retransmit the lost segments. We'll see that in a little while. Well, now let's look at a different version of the receiver for a selective repeat receiver. This is a receiver that does a little more work, but can use the network capacity more effectively when there's loss. So here, the receiver still passes data up to the app in order, but it buffers out of order segments to reduce retransmissions. So instead of having a buffer of size 1, it's going to have a larger buffer, and it will take segments in there even as they're not the next one, and it will hold on to them. So that way, when it later gets the segment that was missing, it will be able to send those segments up to the application in order. The ACK number we use is still going to convey the highest in order segment that's received. So it's still like LAS. It's that bottom edge of the sliding window. Plus, depending on the variation, it's quite common to send hints about which out-of-order segments have or haven't arrived. This is going to allow the sender to do a better job by understanding what packets or segments might have been lost. TCP actually uses a selective repeat design, and we'll see some of the details later on when we get to TCP. But let me say a little more about selective repeat at the receiver yet. I haven't really said how it works. Here's how it works. It has a buffer for up to W segments. W is the same size as the sliding window. That's the largest number of segments which could be outstanding at any time. And we're going to use the same one state variable, the last acknowledgement sent. When you receive segments, if they fit in the window from the next segment, LAS plus 1, or actually any of the next W segments from +1 to +W, then you buffer them. You put them in the buffer you have. Then you look at your buffer and you see if you have any segments in order, starting at LAS +1 and onwards. If you do, you pass up those in order segments to the app and you update LAS to push it up to the highest segment which has been delivered to the app. And then you send an ACK for this LAS, regardless of whether it's a new LAS because it's moved or it's the old LAS. If it's the old LAS, you're really making the channel a little more reliable by repeating the acknowledgement, so that the sender, even if it's lost some ACKs, since every ACK here is really telling you that you received all segments up to and including this segment, if we get any of them, we have some idea what's going on the other side. We don't have to get them all. Okay, so now we've seen the receiver a little bit. We've seen the sender in the normal case. We haven't seen the sender with retransmissions. What happens when there is loss? Well, this is what happens. In the case of the go back end sender, we can simply use a single timer to detect losses. If a segment is not acknowledged after some timeout, then we assume that it's lost. In that case, all segments after it will have been thrown away by the receiver. So we simply start resending the buffered packets from LAR +1, the next acknowledgement which we wanted to receive. So we're going back n. We're basically going back the whole window, up to the whole window. On the other hand, in a selective repeat sender, because we're buffering packets or segments out of order on the receiver on the other side, we can retransmit them individually. So we can have a timer for each different segment, and when that goes off, we can retransmit that segment if that segment hasn't been acknowledged. The hope here is that we'll resend fewer of the segments, because we might time out and send one segment, but if many other higher segments have been received by the receiver, pretty soon we'll get acknowledgements telling us that these new segments have been received, so we won't need to resend them. Okay, so now you've seen the sliding window operation for a couple of these variations. One more detail I need to tell you about the sliding window is the sequence numbers. Remember, for stop and wait, we simply needed two sequence numbers, 0 and 1, and we can alternate between them. That's not going to work for a sliding window size W, because there can be more than 2 packets in the window, and we need different sequence numbers for every packet in the window at least. So how many sequence numbers do we need? Well, for selective repeat, if we're sending up to W packets, then they can be outstanding in the network at one time. We need at least W sequence numbers for these outstanding packets. Now we can also, at the same time, the network can be carrying acknowledgements up to W them for earlier packets which were sent with earlier sequence numbers. Altogether, W plus W, we need at least 2 W sequence numbers. Turns out with go back n, you can need fewer, because we won't have all of those ACKs outstanding at a time. We can only have, an ACK for one thing outstanding at a time. But it doesn't worry too much, because usually we would not get too tight on the number of sequence numbers we need. Typically, sequence numbers would be implemented with an n-bit counter. That's a number that would simply climb up to some power of 2, and just as it is about to get there, it will wrap and go to 0 again. So for instance, an 8-bit counter might count up to 255, 253, 254, 255. That's the highest number you can represent with 8 bits, and then it will wrap and go down to 0, 1, 2, 3 again, and so forth. So it's a modulo counter. As long as we have enough bits to cover the range here, we'll be fine with our sequence numbers. And finally, just to show you a little more about how sliding windows work, we're going to look at a sequence time plot for the sliding number sequences. This graph shows the evolution over time on the y-axis of the sequence number. Time on the x-axis of the sequence number on the y-axis. Now if you look at these curves, this blue curve gives you a line for the transmissions of the sender. And you can see here that the sequence numbers are going up over time. Over time, it's sending newer, more highly numbered segments. There's also another staircase here, and that's for the receiver. These are the acknowledgements coming back. And you can see that after some delay, the ACKs come back for the same number of packets that were already sent. This delay here, sorry, this is when the receiver sends the ACKs. This delay will be D, or the round trip time on 2, because it will take about that long for the segment to go through the network for it to be acknowledged. So that's how you read these diagrams. And now something funny is happening here. We'll look at that in just a minute. Okay, so let's look at it. This is a hypothetical sequence number plot for a go back in scenario. If everything's going fine and there's no loss, we have these two parallel lines or staircases. They're going in fine steps going up. We're sending and we're being acknowledged a short while later. But now something funny happens here. What happens here? Well, we must have loss. That's because the acknowledgement number stops going up. So something's been lost and there's a hole in the receiver. There's some, well, since this is a go back in scenario, the receiver couldn't get the next ACK, and so it's not sending further ACK. So this ACK number is not climbing. What's going to happen then? Well, when maybe this segment was sent, there's no ACK that comes back for it. After some amount of time, this is a timeout, the receiver will work, the sender will work out there's a problem. This timeout is going to be approximately the RTT. I mean, that's the minimum it could be, because that's the shortest amount of time you could take to send a packet and get an ACK back from the other side. So a timeout needs to be longer than that. The RTT is the minimum. But you can see here, if 1/2 was the delay, this is about 2D, which is the RTT. After that time, the receiver, it's hard to work through these things. After that time, the sender will time out and it will start sending these things again. So up through here, these are all retransmissions. That is, they're segments which we sent previously and we're now sending them again. And after another short delay, across here at the bottom, the receiver will start sending acknowledgements for them. And it looks like we get those acknowledgements because we keep climbing up here and there's no more loss and we keep going. So as you can see, there's a lot of information in this time sequence diagram if you know how to read it. This is just one scenario for the possible evolution of a sliding window. There are many others, but I hope from this, this lecture you have a sense of how the sliding window works. Oh, and you can see here I've cleaned it up, and hopefully I've gotten all of those inferences from what's going on correct.